Okay.
Okay.
All right. Good. All right. So we've had some trouble getting started here, and so we've gotten started now. So this is in case you're logged in. This is the chemistry 125. It's the review session for the first exam. And we're just getting started now because we had a little problems. So if you're out there watching this,
Yeah,
okay.
it's a request for some stuff, right? So it's just moving right now. I open it.
Okay. So I see. Apparently Neil Patel has logged in. Yeah, right here. So anyway, so at least one person is out there listening besides the people in the room.
I think he came in and left.
Okay.
It says, yo, is anyone there?
And that happened, yeah.
Okay,
Back
well,
at 6 o'clock.
they know-
So he came in.
Well, they know we're here now. So. Anyway, okay, so we started a little late. If you're out there and you can hear me and you have a question,
There's a little raised hand button.
I guess.
There's a person saying that, someone said, yeah, Kyle raised his hand constantly, Kyle's raising his hand. Yeah.
Okay.
It's you.
All right.
Just raise your hand.
Apparently, there's some way I can communicate with you out there. If not, the way I want to do this is, if you have a problem, certain subject that you want me to discuss, it would be best that if you had a problem associated with that subject, and I have the book here, and just name the problem, and then I'll look it up, and we'll just do it on the board. Okay, so someone wants to do a sapling problem, so that's what we'll do.
This is chapter 1. Like, any of them that I got, like,
Okay, so give me a problem. Yeah.
Which way was it?
number 7. Yeah, so I was just like,
Okay,
why did
so
you start at
we are. Okay, so we're looking at a sapling problem. This is from chapter 1. And we have
Yeah, that's it. Yeah, that's it. I think it's just the actual.
Atom is
Yeah.
So finally, yes, it's
Okay.
just surrounding us.
Okay. So this is from chapter 1. So this is the entropy chapter. And basically the question is to calculate delta S of the system, okay. Delta S of the surrounding. And delta S of the universe. That's pretty easy looking. So we're looking at a chemical reaction. You have to calculate delta S of the system. You know delta H of reaction. So what is delta S? It's going to be delta S is delta H over the temperature at which the reaction takes place, or which the data, the delta H data is available. So this is occurring at 298. So it's basically delta H over 298. So you just divide. Use the correct. So just have to check that. calculator here is actually delta S surroundings. You have to take, if you want delta S surroundings,
Yeah,
it's the heat transfer to the surroundings. You can assume that that happens reversibly because the surroundings are so large. Okay, and this would be positive. Okay, and so your units, so this is in kilojoules per mole. So
Did you
with,
write that, or- So is that what you got from,
this is
just reading,
this is delta S for the surroundings. Is it delta H? This is the heat of the reaction here. And to calculate the delta S, yeah, surroundings. So it's assumed that what happens is the heat transfer is reversible. It's the only way you can just use this heat for this calculation. And since the surroundings is so large, small amount of heat that you're dumping into the surroundings from the reaction, it's assumed that the heat is reversible. In other words, you never change the surroundings to any significant extent when you transfer the surroundings to heat. The concept of reversibility is something you got to think and read about. Okay. Okay, so that's that. We need to replace this here. We'll just walk this. This.
choose a new slide. There you go.
Yeah, I suppose so. Okay. Okay, so now
so that bottom line,
That's the surrounding. It's just the delta H over the temperature. That's
so
what
we just divided it into the.
that's just read the delta utility.
see, now it's-
Just the next happening.
I think there is actually.
I just don't understand why it's so difficult to erase. Okay, I see. You have to put it on a new one. I'm using how to learn how to use it. If you press it too flat, it doesn't work. So on an angle, it works. Okay. Now, so how would you calculate delta F in the system? This is where you would go to the table. You would just use. So this is going to be basically you're going to go to the table and look up these S values. So this would be basically S of the product, and S of the reactants. Okay. And so you want to write it out something like this. And you have, you're going to look up the entropy of aluminum, solid aluminum, the standard state. Okay. What is that? Can anyone tell me what that is? Oh, I see.
You might just graph it.
Okay. Okay. Well, anyway, so you won't go into, I'll just give you the general solution. So it would be, so it would be 4 times the S of aluminum solid, right? Plus 3 times, and some of these are might be 0. I have to look them up. So this would be S of the oxygen gas minus 2 times the S of the Al2O3. So basically, you've seen that kind of equation before. We did it with enthalpies of the reaction. Oh, yeah, that's right. This is actually backwards. This should be products minus reactants. So this actually falls over here. Okay, just let me show you that. So it's always final minus initial. Yeah, so it's product exponential. So, yeah, and so you have to, well, yeah, because you're going to look it up for just a single molecule, right? So it's Al2, O3, this is going to be entropy, right? This is entropy. See, this is why I prefer to just go like this. 4A, 3B, 2C. So I can say 2 times entropy C minus the sum 4 times the entropy of A minus 3 times the entropy of C. Okay. So you've seen that before. Right? So it's this involves you having to go to the table.
Wait, wasn't that the plus inside?
Oh yes, right. So it involves you having to go to the table, of course. And so and you have to be careful when you look at the table. Make sure you get the values right. There's phases involved. It's liquid, it's gas. That comes into play with water a lot. So that's pretty straight. This is all pretty straightforward. Then it's very simple to calculate so very simple to calculate the entropy of the universe. Entropy of the universe, the change in entropy of the universe, delta S system plus delta S surrounding. And in order for process to be spontaneous, the entropy of the universe is found. In order for criteria of spontaneous change, is that the entropy of the universe must increase.
So it's supposed to be positive or?
Yeah, the entropy of the universe must be positive. Now, the it doesn't matter. I mean, it's possible for the entropy of the system to decrease or increase and still have spontaneous change. That's where the Gibbs-free energy comes in, which takes into account really two factors. Two factors: the change in enthalpy for the process and the change in entropy. And you have to combine those two factors, and they're combined in the Gibbs-free energy. So now all of these factors are for the system. So this is delta H, delta S of the system. And this is T is the temperature at which the process takes place. So in order for this to be spontaneous, this delta G should be negative for the process. So that's what we want to keep in mind. So there's really 4 cases that you should be familiar with. Where delta H is positive or negative, and delta S is positive or negative. For example, if delta H is positive, that does not contribute to a negative delta G. Simultaneously, if delta S is positive, that's going to contribute to a negative delta G. So in the case where you have positive delta H and a positive delta S, you could still have a spontaneous process. That's likely to happen at a higher or lower temperature. See, that's an important question that you have to understand this. Let's say delta H is positive. That does not favor spontaneity, does it? And then the thermal process.
So you want coefficients to be negative
Yes.
in order for spontaneity?
Right. It's very important to understand this. So if delta S is positive, then you can see this whole contribution would be negative, and that's good. Okay. Now, in order for this term on the right to overcome, say, a positive delta H, the greater the temperatures can only be positive, right? That's from 0 to infinity, it can't be negative. The greater the temperature, the more likely that this term is going to outweigh the first term, and you're going to have a spontaneous process, right?
If it's high.
Right, right. If T increases, it can overcome this delta H of power. Okay? So you want to be familiar with all these four cases. That was the first case. So we did, so the cases are, positive, positive. And now this is covered well in the book, and it's actually in the table in the first chapter. And I'll find it. I'll find the page before we leave this.
It's question 9.
Okay. So consider if this is positive, delta H is positive. If delta S is negative, then this term is always going to be positive. So in that case, both terms are always positive. Delta G can therefore never be negative. And delta G is not going to indicate a spontaneous process. Okay? So let me just find the case. It's in chapter 4. Okay. Chapter 1. Okay. So you should see table 1.1. That's in chapter 1. That summarizes it. So let's look at like a third case. And I'm not doing this in the exact order of that table. So if delta H is negative, that lends itself to a negative delta G, correct?
No, you can just calculate actually.
Okay, we'll do a problem in a minute. Let me just finish all this case. So if that's negative, that would contribute to delta H. Delta H would be negative, contribute to a negative delta G. If delta S is positive, that's going to contribute to a negative delta G. So that's, no matter, you'll have a spontaneous process at all temperatures. So let's consider the last case. We have negative, negative. So we have a negative delta H and a negative delta S. So who can tell me at what temperature a spontaneous process would be? A high, I mean just a higher, I don't mean what temperature, just lower temperature? High, okay, so negative is good and delta H. The negative delta S makes this whole term positive, right? That's not good. You want the temperature lower. Right? If the temperature's high and this whole term is positive, it's going to overcome the negative delta H. Does everyone understand that? Yeah, if delta S is negative, and this whole term is always going to be positive. And to make it, and you want its magnitude to be lower, right? So therefore you want it to be a low temperature. Right? Otherwise it's going to overcome this one. Right? So you should, on any of these, general chemistry exams that cover this topic, you'll always get some question that covers these cases, right? Where you'll be asked whether spontaneous reaction is favored by a high or low temperature. So you should get, it's a very simple analysis. You should know how to do that. And they discuss it in chapter 1 thoroughly. So now we'll move on to another problem. So
So on the top, on the very top, and then just slide the screen.
all right, so now we'll move on and do another question. No one's ringed in.
No, it's just
Okay.
recording so someone else can get it.
Okay.
Oh, really?
It says recording at the top, right? So the meeting session is being recorded. So
Okay. So let's move on. Here's the question. Here's a question someone has asked. So for a particular reaction, delta H is given.
You're still in bounce mode.
You can actually do it on here, if you press enter.
What? Roger? Okay. All right, so this is good.
Yeah.
Honestly, that's one detail. Paper faces.
So you're given the delta H for a reaction. And you're given a delta F. Then you're asked to calculate delta G for the reaction at 298. So you have to be careful with the units here, these units. So you're asked to calculate delta G and then interpret the sign, interpret the meaning of delta G. So it's pretty straightforward. So it's delta G equals delta H, okay, minus T delta S. Okay. This is the temperature. Okay. So you have
Okay. I was about to say that, like,
I'm glad you know.
what are you doing?
Yeah.
Yeah, well, this is like, and it has different feedback.
So this is
But I'm doing
I'm doing it. Hopefully I have this. Okay, I've got a syntax here on this. This is an unfamiliar.
the bounce, so let's see what
So just someone with the calculator.
This is delta H.
It's negative 89012 divided by 1,000,
Eight, nine,
which is easy, right? It's 89.12. Okay,
yeah.
plus 139.99.
It was 50, 0.978.
Okay, we'll just say 50 point. You say 50. All right, and that's
97.
plus it told you for mole. Right? Now, do we get everything's okay? Okay. So we have to interpret that. They just ask, is it spontaneous or not? It's not spontaneous. So it's pretty straightforward. Hey, how about some more complex questions?
Hey. This is chemistry.
Yeah.
All I did is put in the number of wrong, and then that's what I was
Okay. Like it's really easy to do that.
Okay, let's try and come up with something a little more complex. No one-line closing check.
Alright, hold on, I'm gonna go to chapter 2.
I think when we review the age principle.
That's the stuff.
Okay, that's chapter
Did.
4, you're getting ahead of yourself. Just do
That's what we
chapter
just
2.
did.
Okay, so let's see. Number...
So you guys are confident in the shop age principle?
No,
It's the
we're
stuff
just gonna
we-
get that in a little while.
Okay, you guys will do something first, all right.
Yes, yeah, all 4 chapters, and that's what we just did. Those stuff we haven't seen in months.
Yeah.
All right, you want to go back to chapter 1?
No, we just finished.
You just finished chapter 1, now we're on 2. I said I learned it, I think, months ago.
Okay, do you guys wanna go over...
Did you do good on chapter 2? So my staff is dropping out like.
Yeah, yellow, there's yellow. That's what you think.
Happy for you.
That's what you're teaching us. Because if you didn't think that, I'd be a little frightened and you'd be walking away. There is hydrogen bonding, dipole, and dispersion. It says identify the terms of molecular forces.
Number 6.
Yeah, number 6.
Yeah.
Now,
Okay.
All right, so we have another one, it's a weird question. Would be nice if we could pull this up on here.
I'm just typing in the chat.
You're going to?
Question. Okay, I'll say. And then on the recording.
Okay, I can put this on the board. So this, okay, this is identify intermolecular forces present in each species. So consider NH3. Right? So if you just consider these 4 molecules, so imagine you had a collection of NH3 molecules, and you're asked to identify the intermolecular forces present. You know that NH3 is polar, right? Or you should. Got the lone pair up here, so it's got this polarity. So you know that that has a dipole, and therefore it's going to have dipole-dipole interactions. So one NH3 is going to interact with another NH3. Right? The positive end of a dipole is going to line up with the negative end of the dipole. Something like that, different ways. So those are significant. Dispersion forces, like London dispersion forces, are always present.
Wait, so we just
If it has a strong dipole, so it's going to have dipole dipole. Now, the London dispersion forces, they're always present. They may not be the controlling force.
Okay. So we confirm 2 for NH3.
Now, but what else about NH3?
Yeah.
NH3 should have hydrogen bonds because nitrogen is electronegative, right? So it pulls a lot of these bonds are polarized. So this would be this represents some positive charge here, some negative charge here. So therefore, you had another NH3 molecule. So you want to recognize situations where you can have hydrogen bonding. And so I think that's pretty clear. I'm gonna get rid of that NH3 thing. So so what about so you had this is normal propylene. So CH3, CH2, CH2, OH. Okay, here's an example where you could have London dispersion forces that are significant between another molecule. Right? You could have significant London dispersion forces at these organic ends. These are not. You must consider these sorts of groups like this. You got a carbon, a hydrogen, or a hydrogen rather attached to carbon. These are generally these are just considered non-polar. Okay? Because the difference in electronegativity between these two species is well compared to the other things. So there's no really polarity in here, but there's the London dispersion force. Okay? But what else could you have? If you look at the other end of the molecule, this end is polar. I'm just going to show you. I'm just showing you the end of the molecule. So that end's polar, okay? Just like this. Right? So you can have dipole-dipole interactions. Really, a hydrogen bond is a special form of dipole-dipole interaction. Dipole-dipole interaction involves a hydrogen attached to an electronegative atom. Just a really special type. So you could also have this is another another propanol molecule down here. I haven't drawn the whole thing, but of interest is hydrogen bonding that you can have in alcohol. So it's just another example. So this is actually a good one because it's obvious that all three are there, and that the London forces are more significant here than say this system.
But
They're always present.
and then the HCl wasn't on that.
Oh, we didn't get there. We didn't get there. So yeah. Well,
The land are most part there, but also
so you have to think back to the lab you guys did on. You get the well plates and you dissolve things in the wells. And you had to explain things. Propanol is in one of those, or ethanol. Okay, so we covered this one. CH4 it's a tetrahedral molecule. It's not, these hydrogens are not all on the plane, right? It's tetrahedral. But so if you have these, is this polar at all? No, because these bonds aren't especially polar, and even if they were in a tetrahedral geometry, these would all cancel out. Okay, if there's any polarity. So all you're going to have with that one is just London forces. Okay. It's London forces. So HCl is polar. So you got about drawing it. Because I remember it goes some positive. Okay. So, anyway, just the positives. So this is polar, but it doesn't form hydrogen bonds because of the size of the chlorine. The chlorine is not electronegative. Hydrogen bonds are associated with oxygen, nitrogen, fluorine. So we don't really consider that a hydrogen bond. But it's a dipole dipole. And of course it's got London exclusion. CO is not, CO, the electronegativity difference between these two, between carbon and oxygen, okay, is small enough that we don't really consider that very polar. So it's just dispersion portion. Right? Carbon, periodic carbon, nitrogen, oxygen, they're close to each other, but I mean, so, I mean, there's some. Here, the answer in the sapling says that also categorizes the heck of dipole. So, that's all. You know, when these questions come up, you want to know whether something is polar or not, or some end of it is polar. In the case of the propanol, there's a functional group that has polarity, right? The alcohol is polarity.
You're gonna have to use that letter. Don't use it.
So,
No,
okay. What's the other? Are you sure about that? Okay. Anything else? Okay. All right. This question has to do with classifying these solids, right? So you're close to the ionic, covalent, valid, and molecular. Okay, so potassium chloride, that should be obviously ionic. It's K plus Cl minus, and that time, what's that? Yeah, but we're talking about solids, right? So basically, it's going to crystallize into one of those structures that you guys studied. Maybe simple cubic structure, okay, where it's going to have each one of these is going to be multiple coordinated to the other. Okay? So that's going to be an ionic solid. Now, let's just jump to this case here. It's just carbon on the diamond. Okay. You can't. It's not going to form any ion cell. Okay? Each carbon's in the same oxidation state. It has to be. So this is just a covalent solid. We just have covalent bonds between the carbon atoms. Magnesium, of course, as you recognize, is another. So the molecular solid, chlorine that we're citing as an example, that that's new to me, I'm not sure what you're talking about.
You're saying it's
I've never
two
seen-
non-metal items.
What? It's two non-metals.
Makes it
Well, what's kind of about Okay, well, so the F and CL, that's a mystery. I've never seen anything like that. Okay, so you can answer that question by process of elimination. I mean, at this point, you should be familiarize yourself enough with your applicator to know what the metals are. And just from everyday experience, the means of moving these are metals. The KCl is a salt, sodium chloride. So some of this stuff is just familiarity, it's involuntary memorization. So, oh yeah, so any questions like this should be easy stuff. Well, yeah, okay, well,
You go to like a health care.
easy, isn't it?
You need to help with that Gmail.
All right, so.
Other than that, for chapter 2.
Yeah, that's pretty good.
Chapter 3 was pretty simple.
I think the stuff, when I looked it over, in my memory, we have the most problems with that in chapter 1 or 4. I'd like to spend some time and go over chapter 8. Oh, it's just, well, no, whatever you guys like, doesn't matter. You guys understand equilibrium constant, rest is the partial pressure.
Did you guys have the quizzes uploaded?
I would rather start checking.
Yeah, I'll do it to it. Some of the questions.
I mean, I said from chapter 4 that way. Just check. You have chapter 4 for now. You have to as well. I got 0 idea about it.
Let's do that one. You guys, you got that wrong.
Why don't you talk about the following, please?
Mine's gonna be different here, but it's, okay, at a certain temperature, 0.64 moles of SO3, 0.640 moles of SO3 is placed in a 1.5 liter container.
Okay?
And then the equation given is 2SO3 solid is in equilibrium with, excuse me, the gas, I'm sorry, 2SO3 gas. Sorry. SO3 gas is in equilibrium with 2 SO2 gas and plus O2 plus O2.
Okay.
And at equilibrium, 0.110 moles of O2 is present. And they want the case of that.
How many moles?
0.110
Of O2?
of O2, yes.
0.110.
Yes, at equilibrium, 0.110 moles of O2 is present. Calculate.
Okay. So this is, first thing with these questions is you want to write out the expression. But just write it out in general terms. So Kc is going to be, we have Kc is going to equal C of liquid, so it's going to be the products. We're using concentrations because you said K sub Z. That's how it's true. Concentration squared. The oxygen concentration over SO3 squared. And okay, the squares come from the stoichiometric coefficient. So that's, and it's implied that before you enter these, before you square them, you divide it by the standard concentration of 1 mole per liter. That's why these things always come out universe. It's implied that when you first learn it, you see how that's done, but afterwards you just apply it. So this is universe, even though it doesn't look like it. Now, so the question is, it tells you you've initially placed 0.64 moles of SO3 gas into this 1.5 liter container, right? That's what you've initially done. And then you let some time go by, and you come back. You have to understand what these questions mean. You let some time go by, and you come back, and what information do you have? You're at equilibrium now, and you have 0.110 moles of oxygen, right? So you have to understand the experiment. So let's look at this. What would be a good way to do this would be that you want to look at each one of these terms and be able to fill them out. Right? So at equilibrium, I would have concentration of oxygen at equilibrium is going to equal 0.110 divided by 1.5. This is going to come out in moles per liter. So somebody just give me that.
Point zero seven three
0.07 what?
Oh, 0.07
Okay. All right. So this is, there's your equilibrium concentration of oxygen. Now, I can look at this right away, and just by the reaction stoichiometry, I know that for every 1 mole of oxygen, I should have 2 moles of SO2 gas. Okay. So that means that I must have double the concentration of SO2. So I can immediately write that concentration of SO2 is going to be 0.146. Okay. This is at equilibrium. Okay. So now you know those two values. But, so you have this value, you have this value. You don't have this value. So again, you're going to go to reaction stoichiometry. You told me you put in 0.64 moles of this material initially. You tell me that you made 0.110 moles of oxygen. Right? So what I'm going to do is I'm gonna go to another page because I want to clearly show this, okay?
Huge kind of molarity of the oxygen.
So now let's fill in the value.
So the initial,
So you have your K, what we want to solve. Remember, these are all equilibrium concentrations that we need. Okay. What is the equilibrium concentration of SO2? 0.146, and that's squared. Okay. The equilibrium concentration of oxygen was 0.073. And that's not squared, okay? So, and we know this, that we initially put in 0.64 moles of SO3, right? Okay. So if I take 0.64, this is going to get divided by, you have to use concentrations here, so we are going to divide by 1.5 liters. Let's just do the moles. If I created 0.073 moles of oxygen, how many moles of SO3 did I consume? You consume twice as many, 0.146. Does that make sense?
a little bit less.
Well, okay, somebody says they're lost, so let's take our time on this. We're trying to fill in these values. Okay? We need the last value, which is SO3. Final, yeah, this is all at equilibrium, this concentration, right? Well, I was told that initially I put 0.64 moles of SO3 in this 1.5 liter container. But at equilibrium, I have 0.073 moles of oxygen. That tells me that I must have consumed some of the SO3, correct? So the question is, how much did I consume? Well, you know that you could write this out. If you're confused, when you're taking the test, just write it out. 2 moles of SO3 are consumed per mole of oxygen produced. Right? Okay? I gotta use the writing on this thing. I'll just put 2 moles SO2 per mole of oxygen. I'll let you guys fill in the English yourself. You guys don't know. So 2 moles of SO3 per mole of oxygen. If you set up just a proportionality, there's 0.073 moles of oxygen. Right? You want to solve for X, so it's just 2 times 0.073 comes over here, right? Everybody see that? So that means you've consumed 0.146 moles of your starting material, which was SO3 gas. Okay. Now this has got to be in concentration, so the volume never changes. This is 1.5. All you have to do is math.
The bottom.
What do you got?
The bottom is 0.328.
Okay, so this is 0.328.
It's going to be squared.
It should be squared.
It's going to be squared. So 0.108.
Okay, so 0.108. And so if someone could do the whole calculation, and if you put it in there.
Oh, no, I was, but that's already been done.
Oh, he's talking. You can tell me.
Is that the correct answer? 0.020.
What do we get?
I'm getting 0.0144.
Well, let's just go over it and see if there's any mistake, right?
You don't do the reaction,
Icing table.
yeah, you don't do the ice, the rice.
You don't need to do
Well, he uses that as to show work, so
that. Well,
we might need to.
okay, maybe.
You know how they have those weird
Yeah, you can do this. You can do this. You can do this. You can do this. Let's just. I think you made a math error. This is 0.146 squared. This is 0.073. This is 0.64 minus 0.146 divided by 1.5 squared. But we'll go over it again. I mean, could have made a mistake, but I don't think so. Let's just make sure you gave me the balanced equation. You got 6 oxygen, 4, 6. Okay, 2 sulfur. All right, so the equation's balanced. Now, you told me that initially, we had 0.110 moles of oxygen in equilibrium.
Of O2 with the pet is present, yeah.
Okay, right. So if you divide 0.110 divided by 1.5 liters, that should give you moles per liter. You told me that's 0.073. Take 0.110 moles divided by 1.5 liters.
0.07333.
Okay, so
Oh, you're gonna have to multiply, like, when you do that, you should, that's really where you're doing it. Like, you multiply that by the square, like, 20, is that okay?
It's kind of a big number,
no,
Yeah.
but then I know I can take that.
What are you guys doing? That's one thing. One thing. So this is correct. Right? That's the equilibrium concentration. Right? Okay. Now, this has got to be twice that. Okay? Because you've made, for every 1 mole of oxygen, you made 2 moles of SO2. Okay? So that means if this should be 0.146, this should be squared. Okay? You told me you initially added 0.64 moles of SO3.
Yeah.
Okay? Well, 0.64 minus the 0.146 divided by 1.5.
That's what they're wrapping. So it's. This is how they have to do it. So you got to do it.
Right, we're taking the 0.12.
It's not good.
Certain temperature, 0.64 moles of SO2. 5 equilibrium, 0.11 mole of oxygen present. You know, they're not always correct. I don't see how they could be correct.
That's just bones.
What?
I
Okay,
I gave up.
I've seen, okay, you gave up, it probably because they don't have the correct answer. Right, so, does everyone see that what you're supposed to do, is, okay, what you're supposed to do is, you have to use the reaction stoichiometry to make decisions about things, right?
Ice table.
Or you can use the ice table. Okay.
Well, right.
But I don't, you know,
Okay. Oh, you say
But I remember it, of course I
okay, so, any more questions?
I mean, it's all stuff like that, but I got all of them.
Well, bring me some more, another one.
Okay.
Yeah, I would like to.
Okay, a certain temperature, equilibrium constant for Kc in this reaction is 53.30. So it gives Kc at 53.30. Yeah, exactly.
So if you AC was 53.3?
Yes. And the reaction is H2 gas plus I2 gas is an equilibrium with 2HI gas. Does that make sense? That's what it does. And the KC is
Okay.
at this temperature, zero point 0.4 moles of H2 and 0.4 moles of I2 were placed in a 1 liter container.
Oh, I remember this one.
And it seems so easy. It's like, oh, 1 liter. I did this with my broken umbrella. That's good. We didn't go out that day. It's just,
How big is the container?
1 liter. Oh, no. Yeah, broken. That's what you get after 4 years. But now we just said,
Okay, so you start out with placing 0.4 moles of hydrogen and 0.4 moles of iodine gas,
yes,
okay, in a 1 liter container.
yeah.
Okay, and so the question is, what's the equilibrium concentration?
Oh, I'm sorry. What's the concentration of HI in present equilibrium? Also, what is the molarity of HI? Yeah, the molarity of HI at equilibrium.
Okay, so you want the molarity of HI, but you place 4.4 moles.
Yes.
Okay, well, let's just do this and see what happens. First thing you do is set up the equation. So KC equals product squared concentration of HI squared, right?
It is.
And concentration of hydrogen over the concentration of hydrogen iodine in the denominator, right?
Yes.
Okay. Now, let's think about this a second. You just 53.2, that's true. But at equilibrium, you have the same moles of each one.
It is 0.4. So it's,
No. You told me that you just throw this in.
okay, you're right.
Okay. You guys have to distinguish between the initial conditions, right? And then what equilibrium is going to do. So basically the experiment is you take this many moles of hydrogen, this many moles of iodine, and you put them in this closed vessel. Now you're going to come back later, much later after the whole thing is coming to equilibrium. And then you're going to say, what are the respective concentrations of these? Okay. So what do you know? You know this, that whatever the concentration of hydrogen is, it's got to be the same value. From the reaction stoichiometry. So let's just put this in here. Okay. Now, they ask you for the concentration of HI.
Oh,
Oh, yeah, you're right. You're right.
it's not quadratic.
Yeah. So you got. The point four is already in moles per liter. So
Yes.
we don't have to worry about that.
Well, it is because it's given.
So
That should be a 2x up there.
That's if you don't do that.
no, this is fine. So, right. All right. So.
So I suggest you just take the square root of each side, which would leave you with the square root of 53.3 equals HI.
let's write the, let's just write the equation. I mean, let's write this out. So it's going to be.
New slide, top very top left. Okay.
I've been using just a mouse. Okay. So all we have to do is just write out this equation. It's going to be square root. I'll just keep the numbers out.
Oh, now you're getting it.
We have the square root of KC, right? And one.
Is equal to, no, no,
I want to carry these over. Right?
right here.
1 4 minus
That's
x.
at the bottom.
You guys, this is what.
So, square root of
Oh, well, I mean, I got this in the
Huh?
53.3 is, so 7.3 times 0.4, and then,
Well, we have one equation.
yeah, you could make these I2X. That's what the whole ICE setting up. Because it's, I mean, it's the only way we learn how to do it, so we can do it this other way.
It is. It is.
Because it's changed, twice the change of the H.
Yes.
Well, did you do the whole thing calculation?
Oh, no, I'm trying to do it. So 0.4 gives us 2.9. Okay, so the square root of 53 is 7.3. And then that's times 0.4, which gives us 2.92. And then times x, which gives us 7.3x. Right?
You should just multiply the square root of 53.3 times divided by 2, and then just divide. Yeah. Yeah.
Okay, whatever.
Just, yeah, 2x plus x. Move back up x there. And it's there.
Yeah, it is there, like, so it
Yeah.
is. Like,
All right, so,
it is.
did you calculate it?
I can't follow it, I'm still lost.
Oh, what do you
Wait,
think?
you can't follow?
It's just, no, we're just doing algebra now,
We're
right?
just doing
I'm looking at the first one, you write both sides out of the box.
Okay.
Then what is this KC?
So I bring plus x times kc to this side, okay? This stays here, I pull out an x, and divide by what's left, which is 2 plus the square kc. You see?
And I think this is the part that you get.
I'm with you on the first step, I'm with you on the second step.
this part, you did that, right? That part you
Yes,
get,
that's
right?
just, yeah, the street.
Okay, and so then this is now a like a
Yeah, that's
constant.
it.
And then, but there's an X here, and there's an X here, so you take this, and you add it to this side, over here.
So it becomes,
So it comes to, like, you don't,
so square root of KC 0.4 equals 2x plus x KC.
yeah.
Okay.
And then he vectored this, so this over here equals X times 2 plus the square root of KC. And then he took this and divided this set.
Okay, I'm still when you say you factor that next, I'm sorry.
So there's an X right here,
Yeah.
and there's an X right here.
Yeah.
So he took it out. You see?
Okay, multiplying both sides, okay.
Yeah.
I get you.
There you go.
Is x times an expression,
Yes, I get you now.
Yeah.
and x equals to 0.314. Okay, so what?
You got it?
Okay, I got you.
And then you divide it by that because this is multiplication. So
314.
so this right here is that.
So this equals,
Yeah.
did you plug it in?
Yeah, it's wrong because it's get multiplied by 2 because there's 2 HIs in the problem. In the original problem, it was 2 HI. So I got that 3.14, entered it 5 times, realized I was wrong, got angry, hit solution, I give up, and it turned out it was 2 times.
So what, so what is the, oh, you want-
6.6,
All right, so-
0.628. I lost track of the question, but I didn't, I got to that point.
Okay, so, again, what do you have to do? You have to look at the stoichiometry. The initial amount, and understand you're putting some reactants in, you're going to get consumed. So, it's just, again, start out.
Whoa.
Start out by writing, you have to start out by writing the expression, and then identifying what you have, what's missing, and then writing the proper expression for what you're missing.
It's just that whole like reduce factor. My brain is like I took that next week. I don't think it sense. I think that's a full month. I got it forever. When you like I went to college at Harvard.
Yeah.
So oh, this is horrible. I didn't know it was
Okay, that's not good.
I'm figuring it all out.
Okay.
Moving it all.
All right, so,
You have any quiz questions?
No, I told you.
I told you.
pull up the quiz.
I thought it was good. I'm just trying to figure out what the answer there. I'm not sure what the quiz is. You know what the answer is? Are they on Saturday or are they even to us?
I think they're on Blackboard. Yeah, that wasn't
When you got the state for it. Saturday. Yeah. I'm not so glad. He's in. What was the base average, right? Melody is grand for, is it more per gram?
Modality, granularity, mole, ground,
Yeah.
salt, salt, not in salt, in the bottom.
Right.
It's not in total.
That's not good.
So,
So, molality.
So, modality, have kilograms, milligrams.
code.
No,
Yeah,
just what we
because
saw.
the molarity is weird.
We're all good with the phase diagram, right? Because that was looking at that was pretty simple.
What are you saying?
Okay, solid liquid gas, the triple point is that we're really looking at.
Critical point is for gas.
That,
So you guys know how KP and KC are related?
Thing is RT doesn't
yeah, like go over that again, because I was like, you asked it.
So KP, so if you had the equilibrium constant, and this would only apply to a reaction where everything is in gas state. Right, everything in terms of partial pressure. So to take a test case, let's take an example. So if you had A moles of A in gas and equilibrium and B moles of B in gas. So consider that a situation. So then you could write KP equals the partial pressure of B, and I won't use them. I'll just that this be raised to the small b, right? This would be the partial pressure of A raised to the A.
Yeah.
So that's how you would write it if you were going to write it in terms of KP. If you want to convert that to KC, or rather, you want to get the relationship between KP and KC. So what you want to do is realize PV equals nRT. The partial pressure of the gas would be so some gas I. So say the partial pressure of I would be, you just use ideal gas law. It's moles of I. It's just some general gas. So the pressure is the concentration times R over T. And we're using concentration in moles per liter. We just need the appropriate gas when we do the conversion. Right? So if you look at that, okay, it's basically, this would be the concentration of this gas I, right, times R2. So what could you do then? Substitute this into this general situation we have here. So we would say concentration of B, right, times RT, the entire thing would have to be raised to the B power. Right, because you're plugging this expression into PV. It would have to be raised to the B. Likewise, concentration of A, R2 raised to the small a. So the algebras, you distribute these over each term, over each variable. This B gets, this would be raised to the B, R to the T. Okay, that's algebra. So what would happen there is this. So you have, now you have KP equals concentration of B raised to B, concentration of A raised to A, right? And RT to B, RT raised to A, right? So this term just equals KC. And now it's KP plus KC times RT raised to the B minus A. Which equals delta N.
So do you product to measure that so you must say,
Yeah.
okay, and always be
Wait,
And so,
to the B over A to the A is Casey?
and so the thing is, some people, if you're a little weak in algebra, some people don't realize that for some reason it's, it's lost on them. If 1 over x, x to the negative 1. So RT to the A is, if you bring it up there, it's RT to the negative A. So RT to the B times RT to the negative A, so RT to the B minus A. Right? Okay. That's how you get there. That's how you get there. If you have, if I have A squared over A cubed equals A squared times A to the negative 3 equals A to the 2 minus 3. Just as an example. You should be able to do that really, really quick. Right? You do something. A is cubed down here, you bring it up, it's A to the negative 3. A squared times A to the negative 3 is just A to the 2 minus 3. These are added. You don't cube one or square the other. And that's where this comes from. So is he giving you a formula sheet or on this one?
He's giving us some formula.
He's giving you some, okay. Right, so this is easy. See, here's how he could throw you on. A little bit of a curve, not much. Right? Let's say he says, okay, I'm going to give you this reaction, and I'm going to give you Kc. You calculate. Just tell me what Kp is. So he gives you a reaction, he gives you Kc. And what you could do is count up the change in the moles to calculate delta N.
Are you here for chemistry?
No, sorry, I thought it
What time is it?
was 8.
Well,
Yeah,
yeah, it'll
some
be.
other girl just came in and looked at everyone's bathroom, so
Yeah, I mean, it'll come
Oh,
up. Start
you're in house, sorry. It's okay.
So basically, let's say he gives you something like this, gives you a reaction. It's all gas molecules. And he tells you what Kp is. He tells you what Kc is. So you'd have to calculate B minus A, change in the moles of gas. Raise it to R2 times Kc, okay, to get Kp. And if he could give you Kp and tell you to calculate Kc, how do you do that? Let's say he gives you Kp, he gives you the reaction, and you have to calculate Kc. Just algebra. So you go Kp to RT B minus A equals Kc.
No, the parentheses are on the bottom. There you go.
That's important, okay? Kp divided by this, right, which is just equal to what? Equals Kc equals Kp. Or to the negative delta, or to the negative delta. Catch that? What all we did here was, we want to isolate Kc. Okay? So you divide by RT times RT raised to the B minus A. Okay? But we want to make it look nicer, so we bring this up to the top. Which means that you'd have to multiply this by a negative, so negative B plus A. Which is the same as negative delta N. So you should, yeah, delta N is the final moles of gas minus the initial in general. Right? We just did it for A goes to B, but what if you had A plus B goes to C plus D? Well, you have two gases on the left and two gases on the right. Yeah, we should make sure that we get that. Right? I mean, what is, okay, so what is delta N for? So here, A moles of A equals B moles of B. What is delta N? Change. This is all gases. What is delta N? I mean, it doesn't even have to be gases. Delta N is a change in mole. Okay. How many moles do you have on the left? How many moles do you have on the right? It doesn't have to be gas. It could be anything. What's that?
Okay.
The term delta almost always signifies final minus initial.
It's changed.
So it's going to be C plus D minus E plus D. Right? All right. So we've only got like 4 minutes. Any other questions? Someone got the signage?
Exactly.
Other than that one guy, 5 years.
That's all that was.
4 to 5
That's how much it's paid in this is. You know, I wasn't stick around for 2 hours, but then I turned 5 seconds on it.
That's pretty helpful though.
So then